Hello and welcome to this explainer. Today we're taking a completely fascinating journey deep into the night sky to explore a truly spectacular cosmic neighborhood. We're focusing all our attention on Caldwell 13, also known to a lot of folks as the Phi Cassiopeia cluster, or NGC 457. If you've ever looked up at the constellation Cassiopeia, that famous W shape in the sky, you've looked right toward this stunning collection of stars. Stargazers affectionately call it the Owl Cluster, and today we're going to unpack the incredibly dynamic, frankly almost violent reality of what is actually happening inside it. But we aren't just taking a quick, casual glance today. We are going to ask a very specific, really intriguing question. What happens when astronomers spend 20 years, literally 2 decades, staring relentlessly at a single cluster of stars located 7,900 light-years away? What kind of secrets emerge from the dark when you track the exact same stellar neighborhood for that long? Well, we're about to take a cosmic tour deep into the Perseus arm of the Milky Way to find out.
Okay, let's dive into this. Section 1. Meet the Owl Cluster. So, here is the breathtaking field of NGC 457, and right away what really draws your eye are those two brilliant supergiants, Phi Cassiopeia and HD 7902. These two incredibly bright stars form what look like two glowing eyes, just peering right back at us through the dark. That distinct visual layout is exactly why it earned the nickname the Owl Cluster, or, sometimes people even call it the ET Cluster. It really grounds us perfectly in the visual geography of this region.
And before we go any further, we just have to stop and wrap our minds around the sheer scale of this. 7,900. That is how many light-years away Caldwell 13 sits from our telescopes here on Earth. To put that into perspective, the light we're analyzing right now in this explainer left those stars nearly 8 millennia ago. We are literally looking back in time to watch the behavior of these distant giants. It's basically a time machine.
Section 2. A 20-year cosmic stakeout.
To truly understand a cluster this far away, researchers basically had to act as long-term data detectives. This wasn't some overnight discovery. It was a multi-generational observing campaign spanning 3 distinct windows. It all started back in 1993 with a modest 4-night run. Then, they really stepped it up between 1999 and 2002 with a 31-night survey. Finally, in 2010 to 2011, they conducted a massive, deep, 24-night survey capturing over 4,500 individual frames. The sheer dedication here is wild. But this level of monitoring is exactly what you need to catch stars subtly shifting and changing over time.
So by carefully stacking these overlapping observational fields from the 3 survey runs on top of one another, kind of like a giant cosmic puzzle, researchers meticulously mapped out and monitored a staggering 2,900 stars in this one specific area. So what was the payoff of this massive 2-decade cosmic stakeout? Well, it was huge. They identified 79 total variable stars, which are stars whose brightness noticeably fluctuates over time. And out of those, 66 were brand new, absolutely never before recorded discoveries. They found dozens of complex, multi-periodic pulsators and multiple eclipsing binary systems where stars actually physically block each other's light. And this proves an absolutely crucial point. The night sky is not just a static, quiet painting. It is a violently dynamic, ever-changing environment.
Section 3. The pulsating B-type stars.
Now, these B-type stars are incredibly hot, massive, and exceedingly luminous. They're really the primary characters in our cosmic story today. Among them, astronomers found a huge group of what we call slowly pulsating B, or SPB stars. To make this really complex astrophysics a bit easier to visualize, I want you to think of these stars as having a biological heartbeat. They exhibit something called G-mode pulsations, meaning gravity is the restoring force causing the star to expand and contract. The star is quite literally breathing or pulsing out there in the dark.
Now, what's really interesting about this slide is how thoroughly these B-type stars dominate Caldwell 13. Out of the 79 variable stars they discovered, a massive 45 of them are B-type variables. That is the largest concentration of these hot, pulsing stars found in any open cluster studied in this specific series of surveys. They absolutely define the entire character of this stellar neighborhood.
And you know what makes this even more fascinating? Their age. In cosmic terms, this cluster is practically a newborn baby. It's estimated to be only about 20 million years old. Yet, despite being so incredibly young, the stars inside are fast rotating and wildly fluctuating. It's honestly like a stellar nursery filled with chaotic, highly energetic teenagers.
Section 4. the enigmatic B stars.
To see just how erratic these stars are, we can compare this H-alpha emission data. On the left, we've got data from the early 2000s, and on the right, data from 2013. And this brilliantly illustrates how 4 newly detected B stars actually switch their emission phases completely, on and off between the 2 observation eras. Just imagine a giant star deciding to drastically change its fundamental light signature over the course of a single decade. It's mind-blowing.
So the crucial point for us is understanding why they do this. These B stars are spinning so unbelievably fast that they become unstable at their equators. They actually switch between being a normal star, an emission star, and a volatile shell phase where they literally shed their outer gaseous layers, whipping up a massive, swirling circumstellar disk of material all around themselves.
We actually have a prime example of this caught perfectly in the act. Look at the intense spike right here in this graph. This is the H-alpha emission spectrum of a star named NGC 4576. This single epoch spectrum taken at the Apache Point Observatory proved that this fast-rotating B star is currently trapped right in the middle of a violent shell phase. It is actively throwing off its own material as we watch.
Section 5. The Beta Cephei Binary.
When the data detectives looked closer at the spectrum for our next star, they noticed something incredible. Do you see those distinct dips in the graph? They're doubled. This line doubling is basically the smoking gun of astrophysics. It proves that NGC 457-8 isn't just one star pulsing alone in the dark. It is actually 2 massive stars locked in a tight gravitational orbit around one another.
Let's break down this heavyweight pairing really quick. The brighter component is scorching hot at 23,000 Kelvin and rotates at about 34 kilometers per second. Its partner, the fainter component, is still a blistering 20,000 Kelvin, but it spins much faster, at 52 kilometers per second. Together, this single binary system contains a staggering 15 solar masses of material. That's huge!
And because they are a beta Cephei system, they pulse. The combined light of these 2 massive stars beats with incredibly precise, high-frequency P-mode pulsations, which are driven by pressure inside the star. These Fourier amplitude spectra reveal 2 sharp peaks, representing 2 distinct frequencies of their cosmic heartbeat. It is a highly complex, beautifully rhythmic dance of light.
Conclusion: the living night sky. So the researchers concluded that this cluster is remarkably rich in these incredibly volatile, pulsing, and fast-spinning stars. The grand takeaway from this whole 20-year stakeout is that our universe is fundamentally alive. Stars do not just sit quietly in the dark. They breathe. They shed vast shells of glowing gas. They lock into tight, swirling dances with one another, all while beaming their complex rhythms across 7,900 light-years of empty space straight into our telescopes.
It really makes you view the night sky a little bit differently, doesn't it? Which leaves us with this final thought. If just one single cluster like Caldwell 13 can hide 79 beating stellar hearts and violent stars constantly shedding their outer layers, what other fast-rotating, explosive secrets are just waiting to be discovered, hiding out there in the dark of the Perseus Arm? Keep looking up, keep asking questions, and I'll see you in the next explainer.